introduce Ben Striner, my good friend. Ben's a legend out here, in case you don't know.
Thanks, Piksha.
He's probably the person who's who's had the biggest influence on the course ever. And he won a Nico Haberman Award for his work with the course a couple of last year, a year and a half ago. He has taught the portion of the course that covers GANs pretty much consistently every semester. So maintaining tradition, Ben's back here to teach. He's probably knows a lot more about the subject than I do or I ever will, so there's no one better than me right now to teach the subject. I'll hand over to Ben.
Thank you for that introduction. Hi, everybody. Today we're going to talk about GANs. They are hot. They are awesome. They do amazing things. These are all the really good videos and deep fakes you've been seeing these days. So hopefully this should be a subject that everyone's excited about. I know as soon as I saw them, it's a unique way of handling things that can do kind of incredible things with data. So with that, let's jump into GANs. Just a brief overview we're talking about. We're going to go through the motivation. We're going to talk a little about generative models, what they are, how GANs work, how they get evaluated, how they compare to VAEs, and then we're just going to go through some architectures and different ways you can vary them and make them do interesting things. But to start off with, what are we talking about? GANs are a tool for generative modeling. And you're going to be able to answer questions like, what is a GAN? How do they work? What are the problems they can address? And how do we actually make them work in practice? So that's what we're going to try to cover in this set of 2 lectures. And what they are is a generative network is used to generate samples. Pretty straightforward, but you're talking about an unlabeled distribution. So if I just have X, whatever X is, it might be images, it might be music, it might be text, it might be traffic, it could be anything. Given those samples, you try to understand what's the distribution that's underlying those samples so that you can draw more things from those samples. So if you have a set of people's faces, you can learn a distribution of what's the distribution of faces, and then you can generate new faces. You can generate new music. There's interesting work of you put a bunch of AC/DC music into a GAN, and out comes new songs that sound like AC/DC, but they're not real music that's ever been played before. They're new. And these images are really what we'll mostly be talking about because that's what most of the literature's been about. That's images make really good PDF files and audio data doesn't, but there is work in a lot of different types of media. So great strides in recent years, and we're going to start off by just looking at what's happened over the years, what the results look like before we get into how it happened. So this is the original paper from 2014. When we first started giving these talks, it was really new, and I guess right now it's 4.5, 5 years, but we're going to see what's happened. So the original data was just working on MNIST. You guys have probably seen that before. They're 28 by 28 images of digits. There's the CFAR10 faces data set, whatever. But this is the kind of data they were originally working on. And from a tweet of Ian Goodfellow, who's actually the guy who wrote the first paper back in 2014, made this nice little progression of what's happened over the years. And you see it's like exponential progress. And in 2018, this is a person that does not exist. It's a high-quality, high-resolution image of somebody's face that's brand new, that's imagined from the model. Hallucinated is the word we tend to use. Here's some more examples. These are 512 resolution. People are pushing the resolution up. A couple years ago, you see papers, they're all on these 28 by 28. Sometimes someone scales it up to like 100, but now people are at 500, 1,000 resolution. Very high quality, very sharp images that they're able to generate. And it's not just being able to generate images, it's being able to understand the images. So here's a wonderful example of what I mean by understanding. You can take a celebrity image and you can make them angry, happy, or fearful. You have an image of the input. There's no photo of them being happy or photo of them being sad, whatever, but you can add that to the image. You can make them blonde. The gender swap is kind of funny. Aging people is kind of cool. And these are all new types of models that we can now accomplish with GANs that we couldn't do with discriminative networks and with VAEs and with other methods. There's also a really cool method of, some of the new data sets of very high quality celebrity images. So if you if you think about the low quality images you saw in the first picture, now people are interpolating through very, very high quality, never before seen, non-existent images of faces. And what we're seeing here is walking through the manifold of images. And we're going to unpack that for a second. So there is, these are 1,000 by 1,000. So the input images are 1,000 squared data. And if you went through every single image in there, there are a lot of images, a lot of possible images that are not faces. But what we can do here is we can walk randomly through this large space, but we're only walking along things that are actually images. So that's what we refer to as this manifold that it's learned of a way to kind of flatten out the data set of all images into a pretty simple and understandable space. And you can walk through it, you can permute it, you can do manipulations on it. So you've got a new way to represent your data. And that's basically what these generative models give you. It's not just being able to generate new faces, it's now you know what faces are, you can interpolate between faces, you can do manipulations on faces, and all types of other, like a really deep understanding of the faces is really what we're trying to go for. Another interesting result is image-to-image translation, which is you can take images of sunny days, images of cloudy days, images of and switch them. You can take images of night and make them look like what they would look during the day. You can take images of if there's snow and the trees are bare, and the network can generate what would it look like if those trees had leaves on them. And the results are actually very believable to an ordinary human taking a look. So what are we talking about here? We're talking about generative models. You normally have been talking about what are called discriminative models, unless you're doing HMMs or a couple other things in this course. You probably haven't touched generative models too much. But if you think about your data as like X and Y, your images and your what digits each of those images are, your discriminative networks are trying to predict the outputs from the inputs. Pretty simple. Your generative models are actually trying to understand this joint distribution of X and Y. Why do we do that? Because from the joint distribution, we can still get to P of X given Y, we can calculate P of Y given X, we can calculate the marginal of P of X. There are many more manipulations and calculations we can do if we understand the full joint distribution instead of just the discriminative distribution for the particular task that we're trying to accomplish. However, you have to understand that it's a lot harder, and it sounds a lot harder, because in one case, in a discriminative case, you're talking about put an image in, predict 1 of 10 labels. Pretty easy. In this case, we're talking about, given a label, predict 28 by 28 block of images, and that's in the MNIST case. So you're talking about a much higher dimension when you're trying to predict X instead of when you're trying to predict Y. You're talking about many to one instead of one to many. So it's much harder to do generative networks, but they do have certain advantages and kind of a deeper understanding. So the traditional viewpoint is you should really try to solve your immediate problem, and you shouldn't try to solve a more general problem and then reduce it. So this is Vapnik from VC theory, pretty famous dude. And there is still, I would say, a portion of people that have kind of that viewpoint of it is true that a discriminative network just does what you're trying to accomplish, and it does it quickly, and it's more data efficient than generative networks in some situations. But there are some other viewpoints and asymptotics and arguments that maybe generative models can have better biases than discriminative models. So even if you're just trying to model P of Y given X, modeling it as P of Y and X and then reducing from there does have certain biases that might be better on lower amounts of training samples. So with that being said, we know kind of what we can produce from a GAN and why we want to do it, but now we need to talk about how we can do that. So GANs came about in 2014. The goal is to model, as we said, P of X. So we're just talking the simplest case, unlabeled data. How do I understand what distribution the data comes from? You learn a model that can generate samples from P of X, and it uses 2 adversaries. They're called adversaries because they each have their own loss function, and those loss functions are not in agreement, they're in conflict. And those 2 are called the generator and the discriminator. So I guess, apologize for a lot of text on this slide, but we're going to talk a lot about what the generator is. The generator is P of X given Z. Z is some latent encoding, and you try to map from a latent encoding to images. So what that would look like is I say my latent space is going to be a Gaussian. It's going to be a 2D Gaussian. And I say I want to map from this 2D Gaussian to the entire set of celebrity faces. What that gives you is a mapping from something simple to something very complex. And that mapping defines the manifold that we've been talking about. So the generator can be a deterministic function, which just goes from the latent space to the output space, but we're feeding into that data something like a Gaussian. So the key point here is your Z is something that you have some prior knowledge about, or not knowledge really, some prior decision about. You say, I want my Z to be a Gaussian with 200 dimensions, whatever it is. You can say you want it to be uniform. Doesn't really matter, but you have to know what it is and you have to be able to deal with it. And you generate samples from that, and the samples from that prior, which you understand, are trained to map to whatever your outputs are. The part where it gets tricky is what loss function do you use? Because you're not trying to map a particular x to a particular y. You're trying to map z to a distribution of x's. So suddenly, we're dealing with distributions. If I said you want to compare this image to that image, you could say, do the L2 loss or do the L1 loss or something. You could come up with ways to compare two images. What we're talking about now is I've got a set of images here and a set of images here. How do I compare the two sets of images? And that's where our discriminator comes in. So our generator, what it does, I don't know if I can ask questions about what it does, but the tricky part is how do we train it to do that? Because we don't have training examples of this input from the hidden should be this image in the output. And that's where I have it in red. The traditional loss function, you don't have a traditional loss function. It's not L1, it's not L2. It's a neural network that's calculating a loss. This network is called the discriminator. So the discriminator is this secondary network, and it tells the generator what to do. The discriminator calculates the difference between the real distribution and the fake distribution, the generated distribution. It's called sometimes fake, generated, whatever. But the generator tries to confuse the discriminator. So the way it's classically described is the generator tries to say, that guy over there is real, and that guy over there is generated. And the generator tries to trick this guy into saying that that guy that was generated was really real. So if the discriminator can't tell what's real and what's generated, then that means what's real looks like what's generated. And that's kind of the logic of GANs in a nutshell. If the discriminator can't tell the difference, then the two distributions are the same. If the two distributions are the same, then you are accurately producing data like you want to be producing. But from the perspective of the generator, this discriminator is a loss function. It's just not a traditional loss function. It's a loss function that's built from a neural network. And the last thing to say about the discriminator is at the end of training, it really doesn't do anything. You really should think of it as like the training wheels or the guide or whatever, but the thing that it learns is not necessarily helpful in most cases, other than that it guides the generator. So typically when you're doing a GAN, you're training this pair of things, but when you're using a GAN, the discriminator's in the trash. You're not worried about it. The real goal is to train the generator part. So that was a lot of words, but in images, here's what we have. Random noise from your prior distribution, Gaussian, whatever it is, gets pumped into your generator, and your generator transforms random noise into a random image that is part of the distribution you want. Your discriminator is looking at a stream of real data and a stream of generated data, and it's saying this one's real, this one's fake, whatever. It's trying to make that decision, and the generator is trying to trick it. And since the discriminator is a neural network, you can take the gradient of its outputs with respect to its inputs, just like anything else. Use TensorFlow however you do it, but it's differentiable with respect to both of them. Now, in terms of the actual math we'll get into, this is the original definition of the game, and it has been modified a billion times since, and that's part of what we'll get into. But the very simple game here is a min-max game, and that's always how it's described. Minimum over your generator, maximum over your discriminator. So there's a loss function. Your discriminator is trying to make this loss really, really high. Your generator is trying to make the loss really, really low. And they'll meet somewhere in the middle. And figuring out where that balance is and making that balanced point happen is kind of the trick to GANs. So you see some logs. I think a lot of you might just kind of zone out on that. But this is the cross-entropy loss, binary cross-entropy loss. You're trying to maximize the probability of d of x and trying to maximize the probability of 1 minus d of g of z. So unpacking that, this first term, log d of x, is saying maximize the log probability of real samples, which is x. Expectation under x is your real samples. Maximize the probability of real samples. And the second term, ez, z being your latent distribution, g of z being your generated data, and d of g of z being what does your discriminator say about your generated data, and that's going the other way. So it says make d of x really big, make d of g of z really low. Make your real data high, make your not real data low. Pretty simple. Now what does this give us when we actually break it down? If you were to rewrite these two expectations as a integral, and then you kind of take the derivative to try to find the max, you know, the Calculus 101, you want to find the maximum or the minimum of something, you take the gradient, you set it to 0, you see what happens. So all this is saying is if you take the gradient with respect to any particular point, you set it equal to 0, and then you do some rearrangement, what you end up with is the probability under the real distribution divided by the probability under the generated distribution plus the probability under the real distribution. So real over fake plus real is what the discriminator is going to accomplish. So if your discriminator is trained all the way and your discriminator is perfect, that's what it's going to give you. If we plug that optimal value of the discriminator into the original equation, it actually works out to the Jensen-Shannon divergence between the real and the fake distribution. What this is trying to say is what this combination of two things is doing is it's minimizing the Jensen-Shannon divergence between your real data and your fake data. So if you minimize the divergence between two things, you're trying to make them the same. And the reason this is so complicated and involves these two different guys is you're calculating the Jensen-Shannon divergence between this distribution, which is something you don't have a handle on. The only way you can make this distribution is by sampling data and putting it through a network, but you can still calculate the difference between the two of them by having this two-player game that works back and forth. I'll stop for a second if anyone has questions about this or wants to take a quick look at it.
Discriminator basically is doing a base classifier.
Yeah, it's just trying to find, yeah, if for any given point, what's the probability of this point coming out of the generated data? What's the probability of this point coming out of the real data? And then that's what the discriminator is outputting. It's the ratio between how likely it is from one or the other, which makes a lot of sense. And if it's all the way going to be a discriminator, you're sure it's discriminator, then it'll give one extreme. And if you're sure it's a generator, it'll give you the other extreme. And what the real takeaway from this optimal discriminator is what's the value if PD equals PG, meaning this point is equally likely to be from the generator as from the discriminator. Anyone want to guess? Yes. That gives you 1/2, because if PG is PD, then PD over 2PD is 1/2. So right. But the goal there is if your generated and real distributions match, then your discriminator will pump out 1/2, and everything will be nice and even, and that'll actually give you the minimum to all these equations. And what that's all trying to say is that you're minimizing the JSD under the traditional formulation, which just means make them match. The takeaway is there is a stationary point. That means that if the generated data exactly matches the real data, then the discriminator is going to give you a 0.5 for all inputs. If the two things are the same, then the discriminator is going to say, I don't know if it's this or that, 50% done. And if the discriminator is outputting 50% for everything, then the generator has no reason to do anything, so that's a nice stable point. And that sounds good, right? Because we've got a stable point and that's fine. but don't confuse stable and stationary and what's happening. There is a point that it can balance at, but the data might not necessarily go in that direction. So while you can say, here's a, like, I could take a pencil and I could show you there is, mathematically speaking, a point where I can balance this pencil on a point and it will not move. But that's not saying that if it gets, that's an example of a system that's not stable, because there is a point where it will balance, but if you push it a little bit to one side or the other side, it's going to flop down. So those are two related things, but they're not really equivalent to assume that just because of one, it's the other. So the real problem in GANs is that they may or may not be stable. It depends on a lot of training and what happens and how much you regularize. And that's where a lot of the specifics and a lot of the more detailed research comes in, is trying to stabilize them so that they get to a point. We can prove mathematically that there is a lovely place that they can get to where they match the distribution. The question is, do they get there? Do they converge? Or do they just go about randomly? And the real hard part is you've got these two different parts, this generator and discriminator. You need to train them at the same time. You need to keep them, you can't train just one, you can't train just the other, and the ratio between the two of them affects whether it converges or oscillates or does something silly. So you're trying to hit moving targets on these two different players that are playing against each other, and the research really comes into techniques, tricks, and modifications. In practice, here's some kind of high-level photos of what the gradients tend to look like, which is in your standard GAN. You see in the center of that GAN, there is a place where there aren't any gradients. So that center point is stable, but, I'm sorry, the center point is stationary, but when you look at the gradients around that circle, they're not pointing towards the center in any way. So it's saying there is a point where you can balance, but there aren't really arrows getting you to the point where you balance. And there's just a comparison of a couple different variations of GANs and how some of them will point you towards that center a little faster, a little more efficiently than others. And hyperparameters also have a large effect. So here's a quick demonstration of kind of what GAN training looks like in practice, assuming that loads. So this is just generating random data, and it's slowly converging to find random data, and it pulses back and forth. This is the original kind of style of GAN, and it's trying to learn what the MNIST data set looks like, and eventually it kind of slows down, but it doesn't hit it perfectly. And the details of the parameters and the training are really finely tuned to be able to get to a point where you can really generate data that looks good. But the data looks pretty good. Versus with some tweaking of parameters and not getting the parameters right, you can end up with this, which is pretty much nonsense. But basically, you can end, what people talk about a lot with GANs is just the stability of training, and that sometimes you can hit something that's amazing, and sometimes you can hit something that just kind of oscillates back and forth and looks like nothing whatsoever, really. And it can train forever looking like that. And understanding when to stop, how to train, how to tweak it, is where a lot of the expertise of using GANs tends to come in. So the next few slides I have double starred because these are kind of the real important life lessons, I guess, from GANs, at least from my perspective, what kind of makes me excited about them too. The idea of perceptual loss. We always talk about loss functions as binary cross entropy, or like the L2, the L1, the whatever. There are a lot of loss functions that you can throw around, but now that we're talking about a loss function that a neural network is calculating, then everything about neural networks comes into play. So it's not just the L2. It's, so for example, an example that I think is really easy to understand is, if your discriminator is a CNN and has pooling, and your discriminator is your loss function, then that means your loss function is shift invariant, or your loss function is scale invariant, or whatever you want it to be. So because we're using this discriminator to calculate a function, not only is it letting us deal with distributions, but it's letting us deal with distributions and build in some priors about the architecture and do all the regularization techniques that we've developed for For neural networks, we now apply to the losses that the neural networks are using, which is a really interesting twist on things. So really, if two images are shifted over a little bit, the L2 skyrockets, but to you and me, they look the same. And we've been searching for a good loss function that kind of represents that, and GANs give us a pathway to it. Also, keep in mind, these are implicit distributions, which is you learn a GAN, that means you have a function that goes from z to x, and you can generate z's and put those z's into your function to generate new x's. That doesn't mean you can calculate the probability of x. P of x is implicit. You can generate from P of x, but given a point, you can't say, here's what the P of x is for that point. So it's an implicit distribution, not an explicit distribution. Overall, kind of the good, the bad, and the ugly. Good, GANs make amazing results. Those faces were just awesome, and people are making all kinds of cool things from GANs. The bad is stability, theoretical questions. They're not as theoretically grounded as something like VAEs, but they kind of work. And I guess that's really the ugly, is they just don't have the backing, but it works. And a lot of GANs is built around what works and little tips and tricks. And if you do some smoothing here and you tweak the discriminator that way, then it'll actually work really well. All right. Quick divergence on how are we doing time-wise. I have a thing here. Yeah, just curious. There you go, plenty of time. So GAN evaluation, how do I get back into? Yeah, GAN evaluation is tricky from what I just mentioned, that it only learns an implicit and not an explicit distribution. So a typical GAN task is generate realistic looking images. If you were dealing with the typical data set like Timit, here's some speech, here's some transcripts of the speech, tell me how well you did, you could think of a bunch of different ways to calculate that, and they'd all be pretty straightforward. You know, you talk about the edit distance or whatever. But when you're dealing with GANs, like the task is make images that look like good images. Like how do you judge whether you did that well or not? And that's kind of been an ongoing other this thorn in the heel of GAN research, is the ability to compare research between two people working on GANs is kind of hard, versus if two people are working on classifying images, you go, this guy got 99%, that guy got 98%, he wins. So it does kind of change the way you have to look at things. But there are at least three ways, but three ways we're going to talk about to evaluate GANs. One way is human in the loop, one way is there's some sampling methods for log likelihood, and the third is there's some kind of roundabout methods using neural networks that were designed for other purposes, which are kind of cool. But we'll unpack each of those in order. We'll start with the most basic. Human evaluation makes perfect sense. It's expensive, it's time-consuming, whatever. It's a headache because you're dealing with people, but it legitimately answers the question you want to answer, which is you produce a bunch of celebrity faces, you give it to a bunch of people, and they say, yes, those look like real people, or no, they don't. That gives you a pretty good sense of whether they're realistic or not. It's judging the thing that you're trying to judge. And you know, you can always mechanical Turk, whatever. So this is, in some ways, a kind of last resort or a thing you do at the end or only with your final model. You definitely don't want to be doing human evaluations, you know, every time you train your model every 30 minutes. But it is a very nice icing on the cake to say that this holds water, this holds up to human inspection. We're generating images that really look like images and not just cherry picking. Because, you know, every GAN paper is accused of cherry picking examples, things like that. So now a more complicated method is you can approximate the log likelihood of a test set. That's the way you would handle most discriminative networks, which is like, I want to see how well I'm doing on predicting images. What are the log likelihoods of the input-output pairs that I'm looking at? And what are the likelihoods of everything being produced? That's standard in like text generation. What's the log likelihood of you producing what you're trying to produce? The problem is we can't calculate the log likelihood easily. The way we can calculate the log likelihood is just by generating samples and counting. So, you know, sounds feasible, right? The way to describe that is here's a test image. I want to say, what's the likelihood of my model producing that test image? I can generate 10 billion points from my model and say 15 of those points looked like my image, so therefore the probability of that image was 15 over a billion. Theoretically, it works. That math is completely sound. The problem is, if you're understanding, is just like how many images you might have to generate for that to actually work out. Because basically the method is generate a bunch of data and count how many of that data sets match each of your input points, and then that's the probability of generating those input points. But if you're in a high-dimensional space, like how many cat images would you have to generate an image that looks like this particular cat in your test data set to see what the probability of that is? And it's ridiculous. It's a high-dimensional space. There are so many possible cats. So it is a thing that people have done. It works on certain dimensions. You can do some assumptions to smooth out your distribution. One thing that people do is they convert it into a Gaussian mixture model, which is basically just a bunch of balls throughout the space. So what you do is you say, I'm going to generate 100,000 images. I'm going to put a ball around each image. And then I'm going to pretend like what I've learned is just that Gaussian mixture model. And then you can calculate the log likelihood of that very easily. That's, take a stat class. But that's something that's calculable. It's just, what's the likelihood of this under a Gaussian? There are functions for that. It's just that it requires a lot of data. So it's simple, but the amount of data is gigantic. And it's still an approximation. And a third possible way to kind of do an evaluation of a GAN is to use another network that was trained for something else entirely. And this was actually a very interesting and kind of smart way to do things. And the logic goes like this. You've got a network like Inception. It's been trained to categorize images in 10,000 categories and do whatever it's doing on some other data set with labels. It's a discriminative network. It's just trained to classify images. If you make a GAN that's generating images from this data set, then the images that it generates should be classified by that network that was trained on the real data. And they should be classified in different categories. So basically, like if you had a network that classified pictures of digits as 1 through 10, then you trained a GAN on images. If you put those images into the network, you should get a bunch of things that are 1 through 10. And if they all come out as 5, then you haven't really learned your distribution very well. And if they all come out as very low confidence, then you haven't learned your distribution very well. So you can quantify that in terms of the entropy of the labels that are coming out of your model. So you can't train this way, but you can evaluate this way. That's important to distinguish. But basically what it comes down to is you can take a separate model and see if the stuff that your model produces when it goes into that model goes into categories neatly or comes out looking messy, and the model says, I don't know what this is. So those are 3 reasonable ways to evaluate discriminative network, to evaluate your GANs. None of them are perfect. They all involve a lot of sampling in some way or humans in the loop, but you gotta evaluate them somehow. You can't just put images into a paper and say they look great.
So is the reason we use Inception because it's like a pre-trained model that's available? Like, what's the rationale behind using a specific discriminator to test and a generally trained discriminator?
Well, there are 2 things. Well, okay. First, I'll say that Inception isn't a discriminator. It's a discriminative network. I'm just going to be careful about that. I'm sure that's what you meant. But one fact is that Inception is standard. It's been around for a while. So if I do a GAN and I say Inception score, someone else who has TensorFlow can say slim.inception train, or not even train, like slim.inception evaluate there and just report that model. So, I mean, Inception is just considered broad enough and standard enough, and that was the first paper that did this. If you follow the sites, used Inception, and that's been the one people have used. But like they used Inception 2 score, and then at some point people will start reporting Inception 3 scores. And like the choice of a particular model is just for, why do we all drive on the right side of the road? It's because other people do too. But yeah, theoretically, and especially if you're doing other data sets, then don't use Inception. So like if you were outputting music data, then if you were able to train a music classifier on a data set, then you can use that music classifier to say how well is your music generator doing. The key is this only really works if this discriminative model that you're using, like inception, this inception is using the labels. So the theory only works if your GAN wasn't using the labels. So if you were generating all digits and didn't tell your model what digit was what, but it just happened to come out with 1 through 10, then you'd say that sounds good. But if you were in some ways leaking the information about the digits, then it may or may not be valid. So really, all three of these models have, or all three of these methods have some sort of holes in them.
So now, how do you deal with the situation where the GAN is class specific? So inception is
right, exactly. Like then that wouldn't make any sense because you were training it on generating different labels. So now evaluating it to see if it generated different labels doesn't seem meaningful. So if you did have something where they were like subclasses, then maybe you could do something. But then you'd be stuck with doing something like the approximate test set likelihood. And people don't like doing this very much because like the papers I see on like 32 by 32 images generate like 100,000 images to sample from to fit the GMM. And it's like, I've never seen a paper do this or try to do this on those giant data sets. But the other thing I'll say is a lot of people just don't. I mean, that is a possibility. And especially for these big data sets, if you're generating faces of celebrities, there's no inception for celebrity faces yet. So like if you look through that paper, like they'll show you like training curves and stuff, but there's no hard like, here's the log likelihood of our data set, and if anyone else is working on the data set, they can compare this number to that number and see if they did better or worse. A lot of it's just going to be like, hey, we made some images, you guys made some images. What do you think? So that's kind of what I was talking about in terms of GANs. A lot of it is this kind of engineering-based what works, and like they do work, but in terms of justifying it and quantifying it, there are a lot of places that still need some help. Okay. So at this point, I'm just going to briefly mention VAEs because we are talking about them, I guess, in a week, and they're supposed to be here. Yes?
So the technique to evaluate the test set log likelihood, right? So there can we use a pre-trained model to extract the features of the generated data set and sort of like compute the nearest neighbors with respect to the real data set and extract the nearest ones and sort of like threshold it?
Well, that's kind of what they're doing, although it's not nearest. They're doing like a ball around it and just saying, like, here's a Gaussian. The problem is, like, you're not, especially with GANs, you have one way to, is the other thing. So keep in mind, I can pull Zs. I can take a Gaussian and go from a Gaussian to images. But in the log likelihood of the test set, it's here's the test image. I don't have a good way of saying here's the Z that belongs to it. So that's all part of this implicit that we're talking about, is I can pull Zs and go from Zs to outputs, Xs. But if there's a particular X and you say, what's the probability of this X? Or even what Z generated this X, there's no model going back the other way. If you wanted to figure out what Z generated this X, you would just take all the Zs, put them into your network, and be like, oh, it was this one. So yes, you can solve for what Z goes to what X, but it's just pretty much brute force. Although there are other models we'll talk about that do help try to build those back and forth models. So a lot of this does apply to the original GAN, and there are tons of extensions and there are modifications that we will try to get through between the next few lectures. Sorry. But first, we're just going to briefly mention what GANs versus VAEs. So GANs are what we're talking about now. They minimize the divergence between the target distribution and whatever I'm generating. That's the whole JSD thing we were talking about. There's a divergence measure between these two things. The divergence is very hard to measure, but it involves two different adversaries, and it's not very stable. But that's the divergence. We're going to calculate the divergence. We're going to minimize that divergence. Variational autoencoders say that divergence is way too hard to calculate. But I can get a lower bound on it, and you can use convexity and things like that. So I assume at some point in recitation or lecture, you guys will go through the proofs of that. But basically, VAEs say, here's a simpler problem. We don't need two players. We don't need any of this other stuff. It's a much simpler, much easier thing. So it's not the problem you're trying to solve. It's a bound on that problem, but it's really easy to solve. So in general, you'll kind of see that VAEs are blurrier than GANs, but VAEs work really easily and they work every time. They're a lot simpler to train and a lot of the headaches go away. And in some ways, you can use one or the other for a lot of situations. They're both generative models. I'd suggest try VAE first just because they're easier, and then depending on how that works out, try again. It kind of depends on what you're doing. And there are also some models to try to hybridize the two of them because they do have similar components in them. But these are two different models that are predominant in generative modeling, and just understanding the differences and advantages between them is important. So the VAE, it's basically like an autoencoder. You have input data, your input data gets encoded, and then it gets decoded. And when it gets decoded, the original and the decoded thing should match. So your encoder goes from X to Z, your decoder goes back from, the start of the chain would be your encoder going from X to Z, and then going from Z back to X is your decoder, and you try to make the original X and the final X be the same. That's an encoder. That's pretty simple. What makes it a variational autoencoder is the next part. So far, that's just an encoder. What makes it a variational encoder is the marginal distribution of this encoding should be something you know. So if you're just doing an autoencoder or any MLP or whatever it is, any neural network, your neural network learns hidden representations, but those hidden representations could be anything. Like, I don't know what it is, I don't care. Learn a hidden representation that works. That's all you're saying, that's what you're trying to do. Make something that works. With a VAE, you're saying, learn a hidden representation, and that representation should look like a Gaussian. That's marginally speaking. So that's what you see this expectation down there. So basic stat, if you sum the P of Z given X over all X, you've got the P of Z. So what we're looking at is the P of Z, but the way we calculate the P of Z is the expectation over all X, P of Z of X. And we want to make that match this prior. So we've got a prior that's like a Gaussian, and we've got what's actually happening, which is we encode a bunch of data and we see where our encodings look like. And we want to minimize the divergence between our encoded data and a Gaussian, or whatever it is it's supposed to be. Something simple, this equation right there, that's why it's approximately equal to, is there's a lower bound that we calculate to try to get them to be as similar as we can in a simple way. The pros and cons are really that GANs are a little bit sharper, but VAEs are way faster, way more reliable. VAEs mean you have to understand the prior. So when you're deriving a VAE or running a VAE, part of the equation is the KL divergence between two distributions and what is that analytical divergence. So we know how to calculate the divergence between two Gaussians, and that's why we use them frequently. But you have to understand what's going on. With a GAN, you don't really care about calculating anything analytic. Everything is through a neural network. If you can give me samples, I can do a GAN. So your prior distribution doesn't have to be a Gaussian. It could be a uniform distribution. It could be a spiral. It could be anything you want it to be. And people have done a lot of silly priors just to prove a point, but Gaussians work fine. But it's still a tighter bound. GANs only require that you sample. One disadvantage, though, is that VAEs learn this pair. They're an autoencoder. So you've got an encoder and a decoder. But when you're talking about a GAN, you just have the decoder part or the generator part, whichever you want to call it. At least in the basic GAN. Another big difference is that VAEs have a lot of theoretical justification. If you look at a VAE paper, it's a bunch of proofs and one experiment. If you look at a GAN paper, it's going to be a bunch of experiments and maybe it'll have a proof. But it depends. I'm not going to say all papers, but there's really a zoo of GAN models that are more people just finding, hey, these tweaks here and these tweaks there get us a little closer to what we're trying to do. And another big point about the blurriness, and et cetera, and the validity that you'll maybe understand a little more after a couple lectures is that during training, your VAE goes encode data, then decode data. So your decoding is looking at stuff that was just encoded. Makes sense. When your VAE is generating data, you pull stuff from a prior and put it into the encoder. So when you're evaluating the VAE, the stuff that it's looking at is a different distribution than when you were training it. You hope that they're close enough, but they're not literally the same. Versus in a GAN, when you're training it, you generate from a prior, you put it into the generator, you train. When you're evaluating it, you pull from the prior, you put it in. So the GAN generator is looking at the exact same thing when you're training and evaluating, and that's part of why it's a much tighter, nicer thing. It's, as I said 100 times, it's harder to train, but the thing that it's training is exactly what you want. It's not a lower bound on what you want. Now, some of what we can do with it. So far, we've just been talking about GANs like, here's the P of X, which is your core baseline GAN. But there are so many variations you can do with this whole adversarial idea that let you make different combinations of things. So when someone says GAN, they probably mean like your basic GAN, although all of these things are going to be types of GANs. So it might be an overloaded operator or something. But a GAN, just saying nothing, that's 2014 P of X, I want to generate images given samples of images. They're unlabeled, they're unsupervised. I have an input space and I want to generate more things from that space. That's what a GAN accomplishes. The next step up is something like a conditional GAN. A conditional GAN is I want to generate P of X given Y. You'll compare that to your standard MNIST homework, which is P of Y given X, right? So instead of generating digit numbers given images of digits, you're trying to have a network that, given produce digit 2, it can generate a bunch of 2s. Given 3, it can produce a bunch of 3s. So this is kind of like a GAN, but there are a bunch of different categories that it can produce. The way to modify the original GAN to do this is pretty simple. You just add a Y to the discriminator, you add a Y to the generator. So this generator function, it accepts a hidden sample, the latent prior, and it also accepts a Y. And the discriminator accepts the X and also a Y. So basically, all of the equations and the derivations from the beginning, you just add a conditional into them, and it works out fine. The reason this is more interesting than just training 10 different GANs is that it's conditional. You can actually have a continuous distribution. They're sharing weights. So yes, there are 10 different distributions you're modeling, but they're being modeled by a single GAN and a single discriminator. So all that sharing and regularization helps us out. That's why we like neural networks. The architecture looks something like this. So you just see they appended a Y into everything. So your generator is a function of, takes Z and Y and outputs something. And your discriminator takes those produced X's and Y's and gives you your D. Pretty straightforward. The kind of results we see for those are things like this. It's not very sharp. This was like 2015 or something. But basically what you're trying to see is instead of just generating random numbers, it can generate all the zeros, generate all the ones, generate all the twos, whatever. OK. Building off of these conditional GANs, we have an interesting model called the Laplacian GAN. If you guys have done any image recognition, image processing type stuff before, you might know what a Laplacian is, but it's basically like levels of blurred edges in a document, or in an image. So what it's saying is you can take an image that is varying levels of blurriness and produce that through a GAN. And what it looks like is this, which I wish was a little bit larger. But what we see here is it actually starts from the right going to the left, which I wish they did not do. It's kind of obnoxious. It's like, OK, sorry. But we see over on the right-hand side, they generate a very tiny image. Then one step to the left of that, they generate a slightly larger image conditioned on the previous image. And then a step to the left of that, they generate a slightly larger image based on that slightly blurrier image. Basically, what this looks like is the chain rule. It's you make a small GAN, which says, here's the probability of small images. Then you make a slightly larger GAN, which says, here's the probability of slightly larger images based on the small images. Each GAN just kind of fills in details from the previous scan. And you start with a blurry one, you end up with something pretty sharp. Why would you do this? Well, as we said before, GANs are kind of unstable. If you make the problem simpler, it's going to work better. So instead of trying to solve, make this giant image, you're just trying to solve, make this slightly larger image, or just slightly modify the curves of this image to make it a little bit sharper. Make it a little bit sharper. Each GAN makes things a little bit sharper, and in the end, you've got a sharp image without really having a big leap. Another kind of related idea, I guess, is, oh, sorry.
So in the previous example, you need 4 different GANs?
Yes. Yeah. In this picture, there's 1 GAN, then there are 3 conditional GANs, like the chain rule.
So you need to train 4 different networks?
Yes.
Okay.
Yes, there are 4 different networks. You can train them in series if you want to. This is probably the easiest way to do it, which is, so you've got this big data set of images you want to do. You start by, you blur them all down to like 8 by 8 pixels. You train a network that can generate those 8 by 8 pixels really well. Then you find what are the edges between this 8 by 8 and a 16 by 16, and you generate that portion. You just kind of build it up from there. So it's kind of big, but the fact that you can do them in series does make the overall thing a lot easier. Recurrent networks. Any more questions about that architecture? I thought it was kind of interesting. But you got to keep in mind, once you have this basic tool like a GAN and a conditional GAN, you can make all sorts of combinations of generate this, then generate that based on that. You know, you can generate a sentence, and then based on this sentence, generate another sentence, whatever you want to do. But the combinations are kind of endless. And we're not going to tell you everything that people have done with GANs. We're just trying to show the different ways you can mold everything together. But here's an interesting, yes?
So on the Laplacian GAN, the gradients flow all the way from like the 4th GAN till the 1st one?
In this particular model, they were trained in series, but and then kind of, it's like people used to do with stacked autoencoders. It's the easy way to train it is you train just this guy, then that guy, then that guy. And then when you're done, you can train the whole thing for a little bit to see if it gets a little bit better. So the specifics of that you can play with. This is not the most current architecture. I don't think we're going to get to progressive GANs if you take a look at it, but people have done a lot more detailed things. But the really, really sharp results from the big faces that you saw earlier were actually done by making a small GAN and then just expanding the capacity of that GAN. So it's still 1 GAN, but it's like you just keep adding more and more weights into the net. It's almost like the cascade correlation lecture, which you guys might have had. But yeah, kind of similar to that idea. So like this is not by any means the only way to make big images. But if you look through like the list of accepted papers at NIPS or ICML or something for the last couple of years, it's like flooded. It's kind of crazy, but that explains the first picture I showed, which was like 2014 to 2018, and just yeah, it's crazy. I don't know how many citations he has by now, but it's got to be ridiculous. Recurrent adversarial networks, not the most, well, yeah, actually pretty interesting if you guys haven't seen something like this before. It's still a GAN, but what's interesting about this one is that instead of producing output, it produces delta C, C standing for canvas, or something like canvas. But basically, instead of outputting all at once, you output delta, and all those deltas get added together. So it's kind of like drawing on a canvas, is the way it's described. But here's the architecture, and they only did it for 3 time steps. So while you, it's funny actually. You see this architecture diagram, but there is no dot dot. It was 3 they went up to, but what you do see is that kind of you can generate an image over several time steps by modifying a canvas, modifying representation to make it slowly better. And that's just something else you can do, because the GAN is just giving you the loss function. Any way you want to produce your images, any kind of stuff you want to throw in there, you're kind of free to do and see what happens, because that's flexible. Categorical GAN, do not confuse this with conditional GAN. You called both CGAN and get really confused. But a categorical GAN is more for clustering and semi-supervised learning. So you can use GANs for clustering, which is probably something you weren't expecting based on generative networks and what we were talking about so far. But you can train a network to actually give multiple labels. And the type of networks they show here, the 3 on the right is their clustering method, and the 2 on the left is different k-means, whatever types of clustering. But because you're using a GAN to represent your GAN now kind of looks like a conditional GAN, but it's inferring what those conditions are. So it's saying, hey, you've got two groups of data. What's the distribution of data 1 and what's the distribution of data 2? The difference between this and the conditional GAN is you're not saying ahead of time, hey, this is data 1, this is data 2. You're saying, hey, guess what's the most likely data 1, data 2. And because it's a GAN, because a GAN can learn any distribution of any shape, you can learn clusterings that are like this circle inside that circle. So the types of clusterings you can learn are potentially, whatever shape you want it to be. And the shape of those clusterings is determined by the shape of your neural network, which you get to play with. Please stop me if there are any particular architectures you want to dig into, but I'll just try to go through each of them. I guess the ones towards the end are probably the most interesting. But an InfoGAN is actually really fascinating because it's fixing the problem of just having a generator. So an InfoGAN is a decoder and an encoder, but the encoder is just partial. What I mean by that is we've got this hidden space that we've been talking about, and you go from the hidden space to your images or whatever it is. In an InfoGAN, you've actually got two parts of the hidden space. One part of the hidden space is your encoding and you care about it. One part of the hidden space is some noise that's, whatever. I don't care about all that noise. And you actually split it up in those two ways that you only care about recovering part of it. The loss function, as written here, is the original loss function, which is V. So they're proposing VI, which stands for V with mutual information. And that VI is the same as your original GAN loss, but it's got this extra term, which is the mutual information. What is that I? It's saying, do the GAN, but you should also be able to recover. So the mutual information between C and G of CG, it's a bit verbose, their language, but our G takes in ZC instead of just Z in their language.
Would it be appropriate to think of it as some kind of a hybrid between VAEs and GANs?
Yeah, there are other ones that are much closer to being a hybrid, but the other way to think of it is you have a GAN, and then you just learn a discriminator going the other way, discriminative network going the other way as well. So the way you do it is you have a GAN going this way, and then going back, you have like an L2 loss. So it's kind of like having a VAE or something, but the difference is like that L2 loss we're talking about now is the reconstruction of the prior, not the reconstruction of the output. So in a VAE, your loss is like the L2 between the original X and the output X. In an InfoGAN, this extra loss we're adding in is like the L2 between your encoding and your original encoding and your new encoding. So in this InfoGAN, you're going hidden representation to output back to hidden representation, versus in your AAE or VAE or whatever, your autoencoder type thing, you're going from input to encoding back to input. So it's getting at the same type of thing, but the order does matter. It makes a different model. Whether one's better or one's worse, feel free to try them. But basically what the idea is, you're adding in the ability that you can recover Z. You want to be able to recover Z is the way it's always described. So your Z goes in to create an image, but you want the Z to be able to come back out. What that means is that you want to disentangle and make your Z meaningful. Actually, that word, it's in quotes. It probably should be like highlighted in balloons or something. But disentangled is a great word. That's something to go for. Whether you actually accomplish it or not, who knows. But that's the idea of, I don't just want an encoding. I want to be able to understand that encoding. I want dimensions of that encoding to have a meaning. And that's what they're trying to show here, which is you develop an encoding of the latent space, and there are 10 dimensions, whatever. If you use an InfoGAN, those dimensions will be meaningful. So when they go through their dimensions and they modify dimension 2, they were like, oh, that changes the rotation, which is pretty cool. So when they move C2 back and forth, the numbers rotate. And it doesn't matter if it's a 3 or an 8 or a 5, whatever it is, moving this dimension can rotate things. There's another dimension which was 3, and that dimension made things bold. So I now have a dimension, and I can say, if this is my 8 and I move along this axis, that's boldness. This axis is rotation. And this is exactly the type of thing that we're looking for from GANs, which is not just I can produce the shape from a Gaussian, whatever. You actually want the Gaussian things to mean something. Like ideally, you have a slider, and the slider says, is he bald or does he have a hat? Is he like whatever it is? But if you can understand what the dimensions are, that's an extra level.
So I have a question about the Cs and how exactly InfoGANs are split up. So you get a partial, or you get an encoding of the input with the partial encoding layers. From there, how is it split into C and noise? Is it just...
They're both data coming in. The difference is only one of them is being reconstructed.
Okay.
So the reason they're doing that is like they don't want to have 100 dimensions that are coming out. So, and you can limit it. So you can say, I've got a bunch of noise and I don't want to reconstruct it, but they're like 3 dimensions and like a couple small things, and I want these to be reconstructible. And then that increases the chance of, you've got 10 sliders that you really care about, and then within those you can have a little noise. So it's just trying to justify that. Hypothetically, you can make all of them C, and you'd still have a model, but whether that would still be interpretable or not, who knows?
So for a regular GAN, you cannot do that. You cannot just change one dimension and see the rotation.
Well, you can change one dimension. The question is whether, moving along, as you saw from the faces, moving along dimensions does change things. The question is, are they disentangled and interpretable? And that's what they're trying to get across here, which is, I've got 2 axes, and this one is rotation, and this one is the width. It's not like this one plus 5 that one is the width, and then like the square root of this guy moving over here plus that dimension is something else. So like there is a representation, and all GANs are learning representation. But you might not be able to see it here, but their figure B, these may be cherry picked, keep an example, but their figure B is a regular GAN, is a regular GAN, and as they change a number, as they change that dimension, the numbers move, but I can't put a word to it. Versus what they're trying to argue is in their examples, this number means digit type. Versus in a regular GAN, this number means something, and I can't fully describe it. Whether it's quite as clean as they say it is, and it works well on images, those are all, critical thinking is important, but it is a step in the right direction. And it also does, aside from the interpretability, just the fact that we can get back to our latent dimension is something that we didn't have in a normal GAN. Okay. So this one is actually really close to a VAE. The justification is basically exactly the same. It's just better. It's better in what it does. It's just not better in getting it to train correctly, as is the story in a lot of these things. So we'll start off by just recap what is a VAE. VAE is you take your input data goes to an encoding, your encoding goes back to your input data or your output space, whatever, that should match your input. So you encode and then you decode, and you want to make the reconstruction match as best as you can. The thing that makes it a VAE is you say that encoding should match a Gaussian or whatever it should be. But you do that through a bound on the KL divergence. In an AAE, you say that my encodings should match my prior, and you do that by putting it through a discriminator. So the differences between this and a GAN. In this case, you've got an encoder and you've got a decoder, and they're both being trained. In the adversarial autoencoder, that N loss you're doing is still L2 loss, or whatever it is originally. It's the reconstruction. It's a standard loss. The place where you're using the GAN isn't for the reconstruction. It's for my latent dimension should match a prior. And that's really the key here, is that you're trying to marginalize over all of the encodings. So, and that marginalization is basically done by gradient descent, is the way you can think of it. As you want to calculate the mean of something. How do you do that? Well, you can train a network to minimize the mean squared error of something, And after a bunch of samples and gradient descent, and it'll converge, and it'll eventually get to where you want it to be. But that's memory efficient, that can handle distributions, et cetera, et cetera. So what we're going for is we're matching the two things. The VAE is the same as the AAE, except the matching is done analytically. It doesn't need a second guy. It just happens, but it's matching a lower bound. And you guys can get into VAE, like how that matches and whatever. Versus the VAE, you're saying these two should be equal. You can regularize it as hard as you want. And that's part of the difference is with the VAE, your KL loss term, you can only turn up so much. Because it's a lower bound, if you turn it up all the way, it'll just go to nothing, because it's not bounding things correctly. Versus in AAE, you're actually optimizing the thing you want to optimize, so you can turn that regularization term up as high as you want, and it's just all still theoretically work correctly. What this means is, since Z, the marginal over the encodings matches your prior, then you can just pull from the prior, put it into your network, and everything works great. This is what it looks like in a more graphical manner. You draw, at the top, you have your autoencoder. You take X's, you encode your X's, and then you decode your X's. That's an autoencoder. Now what we also have is we have this discriminator that's looking at those encodings and random samples from X. So the kind of bottom to middle part is the GAN part of a AAE. The differences between an AAE and a VAE and GANs and the advantages, you get an encoder-decoder pair. It's learning on the latent space. And another interesting thing about the AAE is with a GAN, if your outputs are discrete, it's very hard to do, because your discriminator, which needs to be differentiable, is working on the output space. In an AAE, your discriminator is working on the latent space. So GAN, the discriminator is attached to the input-output stuff. In a AAE, the discriminator is attached to the latent. So if your input-output is discrete, you can still have latent that's continuous, and that means your AAE could work in that situation where a GAN could not, or at least be much harder to do. But one of the disadvantages of the AAE is that whole perceptual distance thing that I'm all excited about, you don't have anymore, because you're still using the L2 distance between your inputs and your outputs. You're just using this fancy discriminator to say that something's a Gaussian, which in some sense seems like a lot of overkill to just say, is it a Gaussian or not? But that's all it's really doing. But an advantage, too, is that the discriminator is working on something very simple. So if I said discriminators are really hard to train, it seems like it would be much harder to train the discriminator to tell the difference between real images and fake images than to train a discriminator to tell the difference between real Gaussians and fake Gaussians. Like those are simple spaces. Can you tell the difference between a real and a fake Gaussian? That's a much simpler discriminator. So AAEs are much easier to train for that reason. In terms of what happens comparing an AAE to a VAE, we see that the adversarial autoencoder, you tell it to make a Gaussian, it makes a Gaussian. The VAE, that's the kind of shape that it makes. It goes towards being a Gaussian, but the encodings are not actually matching a Gaussian. This scatter plot you're looking at right now, that's the marginal distribution of the encodings that you've been talking about. That's expectation over the inputs of the encodings. So you take a bunch of inputs, you encode all of them, you see what they look like. In an AAE, they look exactly like the prior you told them to look like. In the VAE, they try to get there, but that's what happens. I'm going to have to reach the last two models a little bit. But now building on top of that, we're kind of working our way up in terms of size and complexity of models. BiGANs are really elegant, really fancy. They train an encoder and they train a decoder. So this fixes some of the problems that we're talking about with GANs. It's an encoder-decoder pair, and what you do is your discriminator is trying to tell the difference between encoded data and decoded data. So in one case, the input to your discriminator is real images and how you encoded the real images. It's trying to compare that to prior samples of the data and decodings and stuff generated. So it's real priors and stuff generated from the priors compared to real outputs and stuff encoded from those outputs. And if you can't tell the difference between something that's been encoded and something that's been decoded, then your encoder and your decoder are inverses of each other. So you're basically trying to train a pair of networks such that that pair of networks is inverses, and additionally, the inputs on one side are real images, and the outputs on one side are your prior. So if it's true that the input is a Gaussian, the output are your images, and the function from images to outputs is exactly, or from x to z is the same as z to x, then you end up with a pair. And this entire model is trained without any L2, L1 loss, whatever, on these encoders. The entire thing is regularized by a discriminator, and this discriminator is looking at both the encoding and the image at the same time. So it's a very big discriminator, it's a complicated discriminator, but the potential of a model like this is crazy. It gives you the encoder, it gives you the decoder, the full distribution is modeled. Here's kind of what it looks like for the more visual crowd. Features go into the generator and give you generated data, versus real data goes into the encoder and gives you encoded data, and those two pairs of things should be the same distribution. Any questions about BiGANs? All right. I think this is the last ones on the list. I should be right on time, actually. CycleGAN. This one has some really cool results. It's a pair of conditional GANs for what they call image-to-image translation, which I thought sounded pretty funny the first time you say it, because what's image-to-image translation? But that's kind of in the style transfer-y type things that people talk about. But basically, you have one GAN that's trained to produce output image type A from B or B from A, whatever. So your first GAN goes from X to Y. Your second GAN goes from Y to X. In addition, you have this cycle consistency. And that's this reconstruction, which is, I should have had the L1 on the other one. But it's basically the L1 error between your original Y and A of B of Y. So convert it back should be the same as the original. And going in both directions, converting and converting back should be the same as the original, in addition to having the GAN. What does that give you? Crazy stuff like this. Really cool images. You can translate zebras into horses and horses back into zebras. Pretty cool. You can translate Monets into photos, and you can translate photos into Monets. You can translate winter into summer and summer into winter. Now, you might take that for granted for a second, but what you need to understand is, why is a GAN required to do this? Why can't you just train a network? Like, if you had a data set of zebra pictures and paired horse pictures, then you would just train a network to go from one to the other and from one to the other, and you'd be done. And you could do that with like an MLP. You wouldn't need a GAN, you wouldn't need anything. But why doesn't that work? Because there's no data set of images of zebras and images of horses in that exact same position. That doesn't exist. You can't do that. There's a distribution of horse pictures. There's a distribution of zebra pictures. And you're training a function that goes from stuff in the zebra distribution to something in the horse distribution. You don't have this horse goes to this zebra, and there probably isn't one that you have a picture of. Like, you have these pictures of horses, these pictures of zebras. There's nothing in there, but the smoothing that the network does allows you to do it. So there is no paired set. There's no discriminative model that could be able to accomplish this task. But because we're using GANs, we're not just minimizing this picture matches this picture. We can do things to the effect of this distribution looks like this distribution, and suddenly we can make horses look like zebras, which I think is awesome. And references. So for next time, I think we're just going to talk about a lot of the stuff I've alluded to, which is how do we optimize this, and how do we get things to work correctly. So I guess to think about, if we have a minute, I'll just draw up really quickly if there's this thing. OK, so we briefly mentioned that a GAN learns the Jensen-Shannon divergence between two distributions, right? So here's my number line. Here's my x. It's a one-dimensional distribution, OK? let's say this is my real data, and this is my generated data. And these don't have any mutual support. The JSD between these two distributions is log of, or negative log 2, I want to say. And it's log 2. Yeah, it's either log 2 or log 4. I'd have to look. I'd have to write it down for a second. But what we'll see with Jensen's chain of divergence is if your generated distribution is this, or it's this, the JSD is flat. And it only starts being non-flat once there's an intersection. So if we were to move this G back and forth compared to this real data, what we want to have, like if that was what our function was, it would be really easy and it would optimize well. But the function we really end up with looks like that. And that's a lot of why GANs don't work too well, is if you're trying to optimize that guy, it's tricky. And you might say, well, you know, I'll make distributions that aren't so pointy. But what you'll see is that in high dimensions, everything is pointy. If you can have the widest Gaussian in the world with some huge standard deviation. If you're talking about a Gaussian in like 1,000 by 1,000 dimensions, then it's practically speaking a point mass right at the mean. It doesn't go anywhere from that. So everything ends up being very pointy, and when it's pointy, it looks like that. So we can't really optimize to what we want. And we'll talk about how we get around that. Any questions, or you guys good?
So we talked a bit about conditional GANs. So in terms of optimization or the loss function of the space, does conditioning help make the loss curve easier to optimize on, or are there advantages like that?
Well, I mean, it's a simpler problem, which is like instead of trying to generate all images, you're trying to generate this type of image and do it 10 times. You're giving it more information, but it's a different task you're trying to do. If your task was, if you had the labeled data, then it's definitely what you should go for. So if you're trying to generate images and you have the list of images, then you can use it. But then, like you brought up earlier, then suddenly your inception score gets all corrupted and doesn't really mean anything. And also, it just depends on what your data set is. A lot of people are working in very like pure GANs, where it's just like, give me image, I will give you other image. They're not conditioning on anything. They're not like, just what can we understand about just image? Like all I care is a block of data. Versus people like LapGAN and whatever. And yeah, there's a lot of structure you can build into it and build a chain of conditionals and stuff. But the current trend for the past couple of years has just been, as I'm sure you've seen with everything, has been like, is there any way we can take all of our data and put it into a neural network at the same time and then just get an output? Like, that's what deep learning is in a nutshell. And the same thing with GANs is like, with early GANs, there was much more work on trying to do like bits and pieces, versus with some of the stabilization techniques, people have just been making deeper and deeper all at the same time and saying like, just do it. But they've got tons of GPUs and, Yes, so in your normal discriminator, your discriminator is saying, is this real or is this fake? In your categorical GAN, your discriminator has a softmax over like 10 things. So it's trying to say, this is a 1, this is a 2, this is a 5. But if it's generated, it's trying to say, I don't know what it is. So instead of indicating real and fake as 1 and 0, it indicates real and fake as either giving it a categorical label or giving it like a flat. Like if you were doing MNIST, your discriminator would be trying to assign 1 out of 10 categories to everybody. But for the generated data, it's trying to go 0.10 or 0.1, 0.1, 0.1 for everybody and just say, I don't know what digit it is, and try to flatten it out. But you can just quantify that in terms of the entropy. So it's basically your generator should have a high entropy distribution for stuff it doesn't, Your discriminator should have a high entropy distribution for generated data and low entropy distribution for...
Basically quantifying it purely based on the entropy of the discriminator, nothing else.
Right, yeah. And so instead of being its output is 0, 1, its output is a softmax, and then you're saying what's the entropy of the softmax.
So when you're training it, the discriminator is trying to flatten the
flat. It's trying to go flat for the discriminated, or flat for the generated data. And the real data, it's trying to go, this is a 1, this is a 2, this is a 3, whatever. And that's how they build in semi-supervised, which is you can train it just like that and just say, give me high entropy, low entropy. Or for some data that you do have labeled, you could say, discriminator, please label this stuff correctly. And the other stuff, just give it high or low entropy, depending on whether it's discriminator generated. So it's where that paper kind of shines is trying to take a GAN and saying, hey, you can use it for semi-supervised GANs. You can use it for clustering. You can use it for these other things that aren't just, I don't want to say just, but it's not like just given images, make more images. It's categorize things and really trying to, I mean, a lot of these are wishy-washy terms like understanding and interpretability and disentangled, but really the goal of GANs is not just generating data, it's understanding how it functions. What are the factors behind it? Thanks, everybody.
So we're out of time. Thank you very much, Ben.
Yeah, 10, 20, exactly. Wave to the...
We'll see you again on